Hello, my name is Glenn Cowan. Today I'm going to be talking about damping factor modulation in optical receivers. This is work that was carried out by a recently graduated master's student, Priya Minfar. Before I go into the subject today, I'd like to give a little bit of an introduction to myself and some of the research that we're doing at Concordia University. I finished my bachelor's degree in 1999 from the University of Waterloo. And then I went to Columbia University and worked under the supervision of Yanis Tsavidis for my master's and PhD. During that time, I built a 100 square millimeter analog computer that could solve differential equations faster than its digital counterpart. I then had the pleasure of working at the IBM T.J. Watson Research Center, and that's where I first got involved in wireline circuit design. In particular, I was designing ring VCOs for wireline applications. In 2007, I joined Concordia University, where I'm now a professor. And since that time, I've been involved in a number of research topics, both wireline and non-wireline. For those of you who have not yet visited Concordia University, it's located in downtown Montreal. So on this map, you can see that it's a relatively short walk to get from Concordia University down to ETS, up to McGill, over to UQAM, and then around the other side of the mountain to École Polytechnique. So one of the great things that we get to do when we're in a city with a lot of universities is my students can take courses at any one of these schools and have the credits transferred into their degree. Also, with so many universities in town, there's a lot of events where professors are presenting things or students get to interact with people from other schools. I have a number of projects in the area of short-reach optical communication. On the transmit side, we've looked at VCSEL drivers, in particular burst mode operation, asymmetrical equalization, and driving the VCSEL through a short transmission line. On the receive side, we've had a number of projects looking at making optical receivers radiation tolerant by putting in triple modular redundancy, energy efficiency by enabling burst mode and variable data rate operation. And then we've looked at the noise performance of equalizer-based receivers and delved into some link optimization. The final project is high-gain, linear, periodically time-varying optical receivers, and that's what I'm going to be talking about today. I also have a number of non-wireline projects, from contactless ECG measurement circuits, power electronics for aerospace applications, spiking neural network circuits, and sports technology, in particular some sensor systems for hockey, and then mixed signal physical and clonable functions. Of course, I'm always looking for new graduate students, so if any of these topics is of interest to you, please don't hesitate to send me an email. Here are some links to some recent work, and I'll put these links down in the comments for this video. I'm pleased to report, though, that graduates of the lab have found work at a number of different integrated circuit design companies. So the outline of today's talk is I'll first discuss the importance of gain and noise in determining the sensitivity of an optical receiver. Then I'll discuss gain, ISI, and noise trade-offs. Then damping factor trade-offs. So what happens as we increase and decrease the damping factor of a second-order system? We'll then apply that to Shunt-Feedback TIAs. And then we're going to look at the proposed technique where we actually modulate the damping factor and change a linear time invariant, or LTI, circuit into a linear periodically time varying system. So the rest of this is just some notation to discuss the different architectures I'll present. And for each of the architectures, we're going to look at gain, noise, and sensitivity. And then I'll conclude. So the context of this work is a short-reach optical link. So on the left is a number of low-speed lines that are multiplexed together that go to a driver, potentially a clocked driver. And in the links that we're dealing with, this driver is then directly modulating a VCSEL. The optical signal goes through some multimode fiber to the photodetector. And so this receiver is going to need some minimum power. We can define the analog sensitivity of the TIA, or of the front end for that matter, as being a required SNR for a particular bit error rate multiplied by an input referred noise current for the TIA. So this is considering only the noise. Now, the latches in this clock and data recovery system are going to need some minimum peak-to-peak voltage. And that requirement can potentially degrade the sensitivity. So modifying the expression for analog sensitivity, we get this total sensitivity. And to the analog sensitivity, we have to add the effect of this voltage requirement. And so the effect of this voltage requirement is take the required voltage swing at the latch and divide it by the front end gain. So clearly, to make the receiver limited by its analog noise, we need to make the gain high. Making the gain high, though, might require adding a number of these main amplifier stages, which can really drive up the power dissipation of the receiver. So recent research work has asked the question, how do we get the required gain? How do we lower the noise without greatly increasing the power dissipation, or while keeping the power dissipation low? One way we can increase the gain of this Shunt-Feedback TIA is to simply increase the value of its feedback resistance, RF. So if we do that, we'll increase the low frequency gain, but decrease the bandwidth. In the time domain, this manifests itself in the unit pulse response. So we get a higher main cursor, but because the bandwidth has been decreased, the response settles very slowly. We'd like it to settle back down close to 0 within 1 UI, but because of the low bandwidth, the tail of the pulse response persists, and that's going to introduce significant ISI. Now, many research groups have successfully adopted this technique by designing an equalizer that follows the TIA in order to remove that ISI. So this is one way that we can increase the gain, decrease the noise, and improve the sensitivity of the receiver. It's not the focus of our talk today. We're talking about a different approach to increasing the effective gain. So let's take a look at what happens when we change the damping factor of a second order system. So we've got this H of S. It's got a low frequency gain of ADC. It's an all pull response. Let's look at what happens as we decrease the damping factor. So as we decrease the damping factor, we get slightly larger 3 dB bandwidth. So the dashed line is 3 dB down, but we get significantly higher peaking in the frequency response. The transient response, or the unit pulse response, is shown in the bottom left. So we get higher main cursor in the pulse response, higher H0, but the ISI terms are increasing quite a bit. We get this underdamped ringing response. So we can summarize the transient behavior, or the pulse response behavior, in this figure on the bottom left. So as we decrease the damping factor, we see that the height of the main cursor, H0, goes up. The ISI initially drops as we get a little bit of extra bandwidth, but then it increases considerably. If we estimate the eventual vertical eye opening, we'll see that it goes up and then it drops back down here to 0. So the question is there a way we can get the high main cursor of a low damping factor system, but get rid of the oscillatory behavior? So can we somehow introduce higher damping factor in order to avoid that oscillatory behavior? In the figure on the right, we're asking, can we get that high main cursor, but get the low ISI of a more suitably damped system? We've taken a look at the Shunt-Feedback TIA. So this is a very common TIA topology. It has a feedback resistor here, RF. The circuit on the left has been replaced with an inverter as the voltage amplifier, and then the small signal model is shown on the right. So we can derive the transfer function and summarize its key aspects. The low frequency gain is approximately equal to minus RF. It's got a natural frequency and a damping factor. So let's assume that we have a means to change the output resistance. And through that change in output resistance, we can change the damping factor. In particular, we're going to think not so much in terms of output resistance, but in terms of output conductance. So the overall output conductance of that shunt feedback TIA would be the reciprocal of the parallel combination of the two output resistances of those transistors. As we decrease the output conductance, we get wider bandwidth, but more peaking, similar properties to the theoretical second order transfer function, except the transfer function is a little bit different, but we still get a higher main cursor and more ringing. The figure on the bottom right summarizes this, where we are scaling the output conductance. So the far side is a scale factor of 1, meaning that's the original circuit's output conductance. We have a certain damping factor, it's pretty high, not optimal. As we decrease the damping factor, as we decrease the output conductance, the damping factor drops, gets to a more optimal level. ISI drops here. And then as we decrease it further, we get higher main cursor, but more ISI. And the vertical eye opening eventually suffers. Where we're going with this is to blur the line between the periodically time varying D flip-flop and the linear time invariant front end. So a traditional front end is going to be linear time invariant, or maybe some saturating nonlinearity, but it's certainly time invariant. A D flip-flop, on the other hand, is periodically time varying on the clock, and it may have some nonlinear, saturating effects when it regenerates. So rather than have this boundary between the time invariant and the time varying parts, let's feed the clock signal back to the TIA and adjust the TIA synchronously with the data rate. In particular, as we'll see, we're going to vary its damping factor. And then more of the system is going to become a periodically time varying system. And for small signals, we can treat the front end as a linear system. So let's take a look at the proposed implementation. So we've got a differential structure. We have a shunt feedback TIA, and then an inverter-based Cherry Hooper amplifier as a single-stage post amplifier. We have these cross-coupled inverters shown in the blue box, and these are going to be used to change the output conductance of the TIA. Eventually, we're going to modulate them, and that's captured by this squiggly arrow saying we're going to vary the strength of those cross-coupled inverters. Here we have the transistor level implementation. So the inverters have all been replaced with P and N-MOS transistors. The cross-coupled inverters are shown with these explicit cross-coupled inverters, and then we're going to be able to vary their effective strength with this shunt resistance MR1. So we're going to apply a rail-to-rail square wave 50% duty cycle voltage to its gate, and that's going to turn on and off that transistor. So when the transistor's off, the overall output conductance is going to be the G0 of the forward inverter minus the transconductance of the cross-coupled inverter. When MR is on, the output conductance is going to be increased. So we're going to add the conductance of that shunt transistor. And all these simulations that we're going to show have been done in TSMC 65 nanometer technology. On the top right is the small signal model, and this gives a sense of qualitatively and through these simulations how this system's working. So what's happening is the unit interval is starting in a high damping factor mode. And so the output is changing somewhat sluggishly. Then we shut off that transistor and we go into a low damping factor region. And we get a very fast response, and the output increases significantly. Then we go back to a high damping response. So there's some intuition here, like why does the response change quickly when we go back to a high damping factor regime? And the reason is that, when we talk about a transfer function, that's a very much an input-output perspective. And so what we see is that the transfer function from, this node here to the output when we close that switch actually has a fast response. You can also think of it as we're kind of resetting the receiver by closing this switch. Of course, GR has some, it's not infinite. We have some finite resistance, so we're not, just shorting the output, but we're putting it into a high damping factor mode with still fast response from that signal to the output. The goal of this work is to choose the right parameters. So we have to choose the widths of these transistors, to choose the feedback resistance, and choose the width of the modulating resistance, and of course the phase of all these signals. The goal is higher gain and no noise degradation. We consider several design scenarios. A linear time invariant TIA post amplifier, then we're going to make just the TIA periodically time varying, then we're going to make both stages periodically time varying. We're interested in looking at the robustness of this technique to the phase of the TIA modulation and the relative phase of the two modulation signals when they're both present. And we're going to have to adapt the approach to noise analysis as we go. So let's talk a little bit about noise analysis. On the right, we've got the output power spectral density of a shunt-feedback TIA. So what we can do here is we can integrate the output noise. So we take the power spectral density in volts squared per hertz and integrate it to get a number in volts squared. Then we can take the square root of it and we get an RMS voltage in volts. The main reason why we're going to do noise analysis is to estimate the bit error rate. So we can take that RMS noise and compare it to a vertical eye opening. And so if we have a peak-to-peak vertical eye opening, we need an SNR VO divided by the noise to equal 14 for a bit error rate of 10 to the minus 12. Now, when we're comparing circuits that have different gain, we often like to refer that noise to the input using an appropriate gain. And then we'll get an input referred noise current that'll have units of amps, and we can compare that to the input swing. So let's talk a little bit about this input referral business. So the top circuit is a noisy circuit. We can describe that noise in terms of a power spectral density or a single value of RMS noise where we've integrated. Input referral means put a noise source at the input of appropriate value such that the noise at the output of this noiseless circuit is the same in the lower situation as it is in the upper situation. So when we're referring the output power spectral density to the input, we simply divide it by the frequency-dependent gain. The tricky part starts when we want to refer the single RMS value of noise to the input. So again, let's think about why we're doing this. We're doing this to calculate bit error rate. So I've shown an eye diagram here with some ISI. At the output, we're going to compare this vertical eye opening to the output noise to find the bit error rate. Now, if we want to do bit error rate analysis at the input, we're going to compare the noise to the peak-to-peak input. So the peak-to-peak input propagates to the output, to the vertical eye opening, the relevant output quantity, with this quantity I'm calling effective gain. The effective gain is the ratio of vertical eye opening to input peak-to-peak. So therefore, it's this effective gain that we should use to refer the output voltage noise back to the input. We do not use the DC gain. The DC gain is larger than this effective gain, as shown here. And if we use the DC gain to refer the RMS output noise to an RMS input noise, we will underestimate the input noise and underestimate the bit error rate. And so this is the approach we're going to use on the LTI systems. If you're interested in looking more at this discussion of effective gain, please take a look at our 2019 TCAS-1 paper that was written by my former PhD student, Dayaldin Abdulrahman. So in this work, we want to come up with a reference design against which we'll compare our damping factor modulation design. So what we noticed is that with the output conductance that we have for minimum length inverters, we have a G0 that's a bit too high. The damping factor is not optimal. So we went from the I diagram in A to the I diagram in B by adding some small cross-coupled inverters. And you can see here in this discussion of LTI system that adding these cross-coupled inverters improves the noise and improves the sensitivity. However, with just a TIA, the sensitivity is dominated by the output swing requirements. That minimum current is significantly larger than 14 times the RMS noise. So here we have some numbers for a reference design consisting of a TIA and a single cherry Hooper post amplifier. There's no damping factor modulation. It was optimized for sensitivity, and we sort of upsize the forward inverters, add these cross-coupled inverters, and we end up with an overall gain of 15.5 kiloohms. We have an input referred noise current of 1.2 microamps. So although there's considerable ISI, we've arrived at this looking at optimizing the sensitivity. So we tolerate that ISI because we're going to get lower noise and an actual higher vertical eye opening than if we'd lowered the gain. So here we've made this a periodically time varying system by increasing the cross-coupled inverters from 4.5 microns to 11 microns, and then adding this triode region MOSFET MR1. It's modulated with a 50% duty cycle waveform with rise and fall times that are 15% of the unit interval. What we get is a damping factor that goes between this small negative number and a fairly large 1.2. The waveform at the output of the TIA is shown above, and then the waveform at the overall output is shown below. We have almost doubled the effective gain. It went from 15.5 kiloohms to 28.2 kiloohms. Luckily, the design is not that sensitive to the phase offset of this damping modulation signal. So we can move it 1/8 of a unit interval and still have a gain larger than 25 kiloohms. And luckily, the post amplifier can process this relatively unconventional eye diagram. Here we add modulation to the post amplifier as well. So we do the same thing. We increase the cross-coupled inverters and then add that triode region MOSFET across the outputs. And again, we almost double the gain from what we had where we only had damping factor modulation on the TIA. We see that we can move around the phase of the second modulating signal relative to the first one by up to 1/4 of a unit interval and still have a gain larger than 50 kiloohms. Also, increasing the rise and fall times from 15% of the unit interval to 25%, we still get a very high gain. So although we have these full rail square wave signals, the performance of the system is not that sensitive to the steepness of the edges or their phase. So let's take a look at how we do noise analysis for this periodically time varying system. Now recall, the purpose of noise analysis is to estimate the bit error rate of samples. So for the LTI system, we look at the vertical eye opening and then we compare that vertical eye opening to the RMS noise. And the RMS noise that we'll measure is constant as you move along the unit interval because the noise sources have a variance that's constant with respect to time. The statistics of them don't change. In the linear periodically time varying system though, the magnitude of the noise sources varies over the unit interval and their transfer function to the output node also changes over the unit interval. So we have to take a more nuanced look. We evaluate the output noise using this expression. So VO is found through transient noise simulation, where we apply no input. Then, to find the noise, the RMS noise at a particular location in the unit interval, we go a certain offset into each unit interval and compute the statistics of those samples, at a given offset in the unit interval. That offset is tau. So we go through that sequence of points and compute a variance that's a function of tau. The results are shown here in the top right. So for the LTI system, we have constant output noise as you move through the unit interval, shown in red, and we have the vertical eye opening shown in blue. For the periodically time varying system, the vertical eye opening shown in black is much higher. The noise, on the other hand, is higher, but not as much higher as the vertical eye opening increased. So what we see is that the input referred noise dropped from 1.2 microamps in the LTI case down to 0.84 microamps in the periodically time varying case. The results are summarized here. So the variant with a periodically time varying TIA and post amplifier had the lowest noise, the largest vertical eye opening, and the highest gain to power ratio. It also has the best sensitivity. And our sensitivity metric is shown here in the bottom. So it's this minimum current where we consider both analog and digital sensitivities, where we assume we need a 25 millivolt swing at the input of the CDR. So to conclude, we implemented per unit interval damping factor modulation. And this takes advantage of low and high damping factor. Low damping factor to achieve that high main cursor, and then high damping factor that brings the output back down close to zero. We looked at a few different designs, starting with a reference design, where we optimize the output conductance by putting small cross-coupled inverters at the outputs of a Shunt-Feedback TIA and a cherry hooper post amplifier. Then we add this triode region transistor across the outputs and increase the size of the cross-coupled inverters, and that allows us to modulate the damping factor synchronously with incoming data. In the end, that increased the gain by 3.6 when applied to both stages, and it improved the gain to power ratio by 3.2. We also designed a variant that matches the gain but dissipates 40% less power than the reference design. Our future work is going to be concerned with looking at jitter transfer. So how does the output jitter, data jitter, compare to the input data jitter? And does clock jitter get passed on to data jitter? We also have a chip design underway that we're going to tape out and then measure. Here are some of the relevant references. So Perea was the first author on these 3 conference papers, and this shows the full reference to Dea's 2019 TCAS-1 paper on noise analysis. Thank you very much for listening, and if you have any questions, please do not hesitate to send me an email.